Melting ice is an example of, hey, 92% of us had it right. It is an example of a physical change. That's because when we melt ice, what are we starting with?
We're starting off with
water.
Water.
In which phase?
Solid.
Solid phase. And we're ending with?
Water in liquid phase.
Water in liquid phase. So it's water to water. It's an example of a physical change. Okay, couple things here. Let's see. Oh yeah, just getting the Scrata app. I have a demo that we're going to be doing, and those of you that are sitting on the ends of your benches today, you're going to be the first demonstrator for your row, and then you're going to pass those pieces of tape on down to another person in your row, and then it will be the demonstrator for the second portion. And so what we're going to do, I'm going to take some tape, and I should have made some handles. There we go. So I put some handles on there so it does not stick to the end of the table, and you should be able to rip them up off of there. And I'm putting my own tape on here so I can demonstrate for you as well. But again, the person, whoever that tape is next to, is the demonstrator for your row to begin with. Now, one of the things that often happens this time of year is that if you are walking across a carpeted surface, if you're at all like I am, I drag my feet a little bit. And what's going to happen if I approach a metal object? You're going to get a shock, exactly. And that shock occurs because what's happening is a transfer of charge between me and the earth. And it transfers through a metal object that is basically connected to the ground somehow, but there's a transfer of charge that occurs. And so when I drag my feet over the carpeting, and if you're a person who gets an electric shock, you drag something. It might be like when I go to the gas station, I might slide out of the vehicle. When I slide out of the vehicle, then my butt rubs across the seat. That produces some friction, and then you might touch your vehicle or touch the gas pump or something like that, and you'll experience a small shock. Same type of thing occurs. Whenever there's friction that occurs, especially this time of year, then there is some transfer of charge that can occur. And the charge that gets transferred is, those particles are called electrons. Now the thing I don't know is this, is that when electrons are transferred, I don't know whether they're transferred from me to the ground. And I should know this, I've been teaching this stuff for how many years. Whether they're transferred from me to the ground or the ground is transferring them to me. But either way, there's some transfer of charge, electrons, that occurs. So what we're going to do with the piece of tape is this, and don't do it quite yet, but we're going to rip them up off the table. When we rip them up off the table, we're going to cause a transfer of charge, or transfer of electrons to occur. And let's say that the electrons are something that gets transferred to the pieces of tape, because I'm treating them in an identical manner, ripping them off. And if I rip them off and the electrons are transferred to the piece of tape, then at the end, both of the pieces of tape should have the same charge. Okay? But let's assume I was wrong. Let's say that the electrons weren't transferred to the tape, but instead the tape transfers the electrons to the table. If I rip them up and the electrons are transferred to the table, in the end, the two pieces of tape still will have the same charge. So whatever we're doing to them right now, we're causing the piece of tape to have the same charge. What we're going to do then is we'll see how the same charge interacts with each other. So before you rip them off, make sure that your piece of tape is nice and firmly attached to the table. Grab onto the handles that I made for you, and let's go ahead and transfer some charge by ripping them up off the table. And once you rip them up off the table, they might stick to your hand. You can go ahead and pull them back from your hand if you need to. But once you do that, you have your two pieces of tape. Go ahead and bring those two pieces of tape next to each other and try to push the two ends together. And what happens if you try to push the two ends of the piece of tape together?
They try to repel against each other.
They're repelling each other, exactly. They're repelling each other.
Because they're not opposites and opposites.
So what this is telling us is that the like charges will do what to each other?
Try to repel each other.
They'll repel each other, exactly. So now the next thing you want to do, take this and pass them down to another person in your row. It doesn't matter, pass them down to one or two people. And that person then is going to be your next demonstrator. And just make sure that you still are holding on to those handles. What we're going to do next now is we're going to cause these two pieces of tape to acquire the opposite charge. We want them to acquire opposite charges. Now the way that we're going to do that, oh, let's see. Anybody have any ideas how we get them to have charges that are opposite of each other?
Only rip off one really and don't rip off the other.
Okay, but since we ripped them both off the table already, we can't do that. So what else might we do? Okay, well, we could, except if we've done that, that's something we've already done. Here's what we're going to do. Now, be careful with these. And we're going to stick them together. Now, you could put sticky side to smooth side or sticky side to sticky side. It doesn't matter. Either way, it's going to work the same. I like to put sticky side to smooth side because then they're easy to rip apart. So I'm just going to attach the two pieces of tape together. I'm going to leave the two handles on the end here so I have something to pull with. And then what we're going to do is that once you have the handles, we're going to rip the two pieces of tape apart. Now when we do that, what will happen is if one piece of tape loses electrons, the other piece of tape will gain electrons, in which case the two pieces of tape should have charges that are opposite of each other. So take your handles, go ahead and rip them apart. If they stick to your hands or whatever else, go ahead and pull them aside. Then bring the two pieces of tape next to each other.
They should attract.
And you should see that the piece of tape will attract each other. And so now this isn't a one-time thing. If you wish now, go ahead and pass this down to another person in your row and see if you can make the charges the same again. And of course, to make them the same, what do we do to make them the same? Rip them off the table. That wouldn't have to be the table, it could be anything else, but the table's the easiest. So just leave the handles on the end. Press them down against the table, nice and firm. Rip them up off the table.
That one worked a lot better.
And you should be able to see that these pieces of tape will repel each other. So this is our first lesson for today. And by the way, our maintenance staff, they don't like cleaning up wads of tape off the floor. They don't like ripping them up off the table or anywhere else. They like to dump them out of the garbage. Okay, so do not leave the wads of tape behind. If you want, you can leave them in your notebook. If you want to wad them up, you can do it right now and take them to the garbage cans on either side or stick them in your notebook so we don't leave a mess behind for the maintenance staff. Okay, but again, if you want to, you can leave them in your book or whatever. But if you're going to take care of them, take care of them now. But let's just do a quick review here. What do light charges do?
Light charges
They repel. And what do opposite charges do?
attract.
They will attract. So light charges repel, opposite charges attract. And so this is kind of the first lesson then on charge interaction that we'll be using through part of our lecture today and part of it on Thursday. The poles of a magnet are much the same way. If you have a north pole and a north pole, or a south pole and a south pole, if you have light poles of a magnet, those light poles will repel each other. Opposite poles are going to attract each other. So poles of a magnet are the same way when we talk about repelling and attracting. Okay, any questions on the demo? Okay, next up then. Any questions on the demo we did at the end of the hour in our last class? We had the chemical change and physical change, so go through and look at these. Any questions on any of them that we did in the last class period? Anything that maybe you don't understand or still have questions about? Going once? Twice? Okay. Next up, chemical property and physical property. These are a couple terms that we should define. And when we talk about a chemical property, we say that these may be observed. These may be observed when there's a change in chemical composition. So these are properties that may be observed when there's a change in chemical composition. So it's kind of like a chemical change. We have new chemicals at the end compared to what there were at the beginning. And a physical property, these here may be observed when there is no change in chemical composition. So if we were to look at a couple of examples of this, we might talk about, here's an example. We can say that the boiling point of water is 100 degrees Celsius. The boiling point of water is 100 degrees Celsius. Is that a chemical property or a physical property?
Physical.
Physical. Because we're starting with water, we're ending with water. So we don't have to change its composition to observe that. Let's say that we want to say that you're wearing. No, see, I'm getting my colors wrong. This one's easy. The color here is blue. That's an example of a physical property. We're not changing the composition at all. We're just simply stating a property that it has. We could say that iron rusts. Iron rust, that would be an example of a chemical property, because when iron rusts, we are changing its chemical composition. We're starting with a bright, shiny metal, and we're winding up with that brownish, reddish material at the end. So, and that chemical is different than what it is we started with. So with this then, we have a couple questions on your Socrative app. Here would be one example. We're going to say that the density of water is 1.0 grams per milliliter. The density of water is 1.0 grams per milliliter. This is an example of, let's get your answers locked in. 5, 4, 3, 2, 1. Perfect. Perfect. That's one of the first perfects you had here. And then we can say hydrogen is explosive in the presence of oxygen gas. That was one that we did on day 1 in here, and we saw the exploding balloon. And we'll count down here. 5, 4, 3, 2, 1. And this here would be an example of a chemical property. How about if we said that helium is an inert gas? The word inert means it does not react, combine with any other chemical. So if we say that helium is an inert gas, that one might be a little tricky. That's a chemical property. So even though, if we go back to the definition, we maybe need to modify that definition just a bit. So we come back to the definition. It says, may observe when there is a change in chemical composition. We could also say, or if there's an attempt to change the chemical composition. Because the fact that helium is inert, even though it can never change its composition, helium is helium is helium. It can never combine with anything. The fact that it doesn't combine with anything is still an example of a chemical property, because of the fact that it's a way that we're trying to interact with chemicals. Okay, so any questions on properties? Okay, then we have the terms endothermic and exothermic. And in order to talk about endothermic and exothermic, we define them like this. We say that an exothermic process is one that
Gives off heat.
gives off. So we say that it releases energy to the surroundings. And an endothermic process is one that absorbs energy from the surroundings. And this is one that's often confused here, but I'm going to underline the word surroundings, and we want to make this distinction here that the system and the surroundings are not the same thing. The system and surroundings, they're different from each other. And so when we look at a chemical reaction, we want to tell whether something is endothermic or exothermic. You and I are always going to be a part of which piece? The system or the surroundings? We're going to always be a part of the surroundings. So whenever we observe something, you and I are in the surroundings of whatever it is that we're observing. Or if somebody's observing you, then somebody else is going to be in the surroundings of you. So you and I always observe what happens to the surroundings. And based on what happens to the surroundings, we make a judgment of what happens to the system. So if a process releases energy to the surroundings, let's think of heat energy. If something releases heat energy to the surroundings, what do you and I feel? Is the temperature going to change?
Yes.
And how will it change?
Will increase.
It should go up. So in an exothermic process, we'll observe a temperature increase in the surroundings. And in an endothermic process, we're going to observe a temperature decrease in the surroundings. So if we think back to day one, we had the exploding hydrogen balloon in here. The exploding hydrogen balloon, is that endothermic or is it exothermic?
Exothermic.
That's definitely an exothermic, because anybody that's in the surroundings, especially if you were up front here, what did you feel?
We felt more heat.
You felt a lot more heat coming off of that because it was releasing heat to the surroundings. You place an ice cube in your hand. What happens to that ice cube? It melts. And as it melts, what is happening to the temperature of your hand?
It's going to make it colder.
It's getting colder. So in order to melt that ice, melting ice would be an example of an endothermic process, because it is absorbing energy out of your hand in order to melt. And so again, the surroundings are getting colder in terms of their temperature. So chemists, when we look at chemical reactions, all chemical reactions are either endothermic or exothermic. Sometimes we don't observe that change very easily because that change in energy is so small, but it is actually the driving force behind chemical reactions. Chemical reaction cannot take place unless there's some sort of change in that energy. So next up then, what we're going to look at is that we have a figure here. And this figure comes from page 61 of your text, if you have that available. And what this is a way that chemists classify matter. We classify matter based on how it's present either as a pure substance or as a mixture of substances. And when we look at something that we say is a pure substances we say have a definite composition. Definite or fixed composition. While a mixture, on the other hand, over here, mixtures we say have a variable composition. And when a chemist uses the word substance, the word substance actually implies that it's something that is pure. So I need a different color here. We'll put in black. There we go. So the word substance implies pure. So the fact actually that we refer to pure substance, that's a redundant thing. If we simply use the word substance, we could say that matter can be separated into substances and mixtures. And if we say that it's a substance, that implies that it is pure. And substances themselves are broken down into two categories. They are elements and compounds. And so if we look at the elements, where do we find the elements? Where's the example of the elements? Where can we find a list of them?
Periodic table.
Yeah, over here on the periodic table. So if we look at the periodic table, the one on the wall here is showing 112 elements. If you pull out the one that we had in class, and I'm going to ask you to pull it out right now because we'll be using this. There we go. This one here is showing 118 elements. And I've forgotten to update the one here on my handouts to show the symbols of the new elements that we know of today. Looks like this one doesn't have them either. That's all right. Anybody need a copy of the periodic table? And I always say you can never have too many periodic tables. We'll be passing these out all semester long, and you'll probably have about 10 or 15 by the time the semester's over. Anybody else need one? Okay. Anybody else? All right. So this here is a comprehensive list of the 118 elements we know of today. We have fixed, however, these 3 elements or 4 elements with symbols, and I don't have them off the top of my head. So who has the periodic table from day 1? Element 113 is which symbol?
NH.
NH. And 115 is?
MC.
MC. 117 is?
TS.
TS. And 118 is?
OG.
OG. And I don't even remember what they all come from. But anyhow, these are the ones that we have assigned names and symbols to here. And this is something that's just been done in the last, confirmed in the last like 3-4 months. There was a statement that came out from the International Union of Pure and Applied Chemistry that confirmed these names as something that will now represent our scientific body. But there are no more than 118 elements that are known today. So when you look at this list here, we talk about elements, we know of 118 different elements today. The compounds, on the other hand, these here are combinations of elements in fixed whole number ratios. So an example that this is showing here, this is showing, I believe this is showing sucrose sugar. So if it's showing sucrose sugar, the formula for sucrose sugar is C12H22O11. But another example of a compound would be something like this. This here is
Salt.
salt. Formula, I heard it was NaCl. Exactly. NaCl, which is our sodium chloride. And so when we write a formula like this, NaCl, this is telling us we have 1 sodium atom for every 1 chlorine atom. So these compounds then are combinations of elements in these fixed whole number ratios. Then we have mixtures over here. We have homogeneous mixtures and heterogeneous mixtures. These prefixes, homo and hetero, stand for alike and different. And so if we talk about a homogeneous mixture, this means that it is alike all the way through. So if we took a sample out, and I don't have one here with me today, but if we go back to where we were at the end of class last Thursday, when I mixed the sugar and water together and stirred it together, you would have looked at it, and if you looked at sugar water, it would appear as if it was one substance. But it wasn't one substance, it was actually 2 substances. It was sugar and water. And so we could make different types of sugar solutions simply by dissolving. We could put a pinch of sugar in a big container, or we could put in several spoonfuls of sugar into the same size container, and both of them would be examples of sugar solutions. And that's why we say their composition is variable. But a homogeneous mixture is one that when you look at it, it appears as if it's one, but it's actually a multiple of them. Whereas in a heterogeneous mixture is one that is very obviously comprised of more than one substance. If you take a tossed salad, for example, or garden salad, and you look at it, you can very clearly see that there's a mixture of different things that's in there. If it's very obvious, that would be an example of something that is heterogeneous. So with these then, I think I have one that is coming up on your Socrative app next. Which of the following is an example of a pure substance? And if you believe that there's more than one answer, then select more than one. But your choices are white bread, seawater, deionized water, which is the stuff that comes out of here, air, and water. Or, no, air and honey, I guess it is. So talk with the neighbor here if you need to. We'll give you about 20 or 30 seconds. All right, so get your answers locked in. And we'll count down. 5, 4, 3, 2, 1. Correct choice here is and only one. It is deionized water. That's because deionized water is also pure water. Okay? So if we have pure water, what is the formula for water? H2O. Exactly. Water would be an example. H2O. Water is always comprised of 2 hydrogen atoms for every
oxygen.
1 oxygen atom. So 2 hydrogen atoms to 1 oxygen. Formula is H2O. Okay, well, Chapter 3 is kind of a hodgepodge of things. Chapter 3 wraps up by looking at some temperature conversions. So what I'd like for you to do now is to take some time and do these 3 temperature conversions. They are, first one, we'll take 25 degrees Celsius and we'll convert it to kelvins. We'll take the second one here. We'll take negative 40.0 degrees Fahrenheit and we'll convert this one here to degrees Celsius. And our last one, number 3, we're going to convert 37.0 degrees Celsius to degrees Fahrenheit. And to do this one, you do need your conversion sheet. And so that's going to be on the flip side of your periodic table. You're going to find these temperature conversions over here. And just so you know, it talks about mass, length, volume, and area. These are good out to 4 significant figures. These temperature conversions, these are exact. And if they are exact, they have no impact on the number of significant figures in your answer. So let's go ahead and apply those formulas. I'm going to give you about 5, 6, 7 minutes, thereabouts, to do these calculations.
That's so weird.
All right, let's go ahead and start getting these into the Socrative system. We are now going to, for the first one, get your answer input. 25 degrees Celsius is how many kelvins? Remember significant figures. All right, we'll give you about 5 seconds here to get them locked in. And we'll count down. 5, 4, 3, 2, 1. Your answer should be 298. Not 30, not 300, not 298.15, but with the correct number of significant figures, it should be 298. And the reason why it's 298 is because when you add and subtract, you don't look at significant figures, you look at decimal places. So you take 25 plus 273.15. The uncertain digit here is the 5. If this is the uncertain digit, we sum them together, we get 298. That makes this digit uncertain. We put in 298. Go to the next one. Get your answer put in. Once again, correct number of significant figures or decimal places. Negative 40 degrees Fahrenheit is how many degrees Celsius? And we're going to get our answers locked in here. We'll count down. 5, 4, 3, 2, 1. And it should be negative 40.0. Negative 40.0. And that, of course, is because the temperature conversions, we said that these temperature conversions are exact. So we're taking it out to the 10th. We wind up going out to the 10th here on these. We do, of course, follow our order of operations, but you're going to wind up with a negative 40.0 on this one here. And then the last one, 37.0 degrees Celsius. This one here is how many degrees Fahrenheit? There's a reason why I picked out this temperature. So I'll get it put in. Remember, the units are already provided for you. You just need to enter in a number. And then we'll count down. 5, 4, 3, 2, 1. And we come up with 98.6. 98.6. And why do you think I picked that number? Normal body temperature, exactly. So if you're traveling in a foreign country, traveling abroad, and they measure your temperature as 39 degrees Celsius, you would then say, got a problem because you got a fever. Right? So again, normal body temperature, 37.0 degrees Celsius. Any questions on any of these three? Going once, twice. Okay, our next topic is going to be atomic theory. We're moving on to chapter 4, atomic theory. And atomic theory the ideas actually go back to a Greek philosopher by the name of Democritus, and there's other cultures that have come up with the same thing. But the word atom comes from the Greek word atomos, who was named in honor of Democritus, who came up with this idea some 2,500 years earlier. The problem is that while Democritus was a philosopher, his ideas were not entirely accepted. For one thing, there was no evidence. It was just something that one theorized or philosophized about without having the actual evidence. But the first atomic theory based on scientific evidence, the first modern atomic theory, and we'll put modern in quotes because it's not quite so modern anymore, based on scientific evidence, was proposed by a scientist of the name John Dalton. And he did so in about 1808. Now, just so you know in here, I do not test on names and dates. This is not a history class, this is a science class. So we're going to be talking about the scientific evidence that is pointed to for the existence of the atomic theory. And in your textbook, if we were to look at the atomic theory, and I didn't pull this up here before class, but I'm sure we can find this early on in chapter 4. And so I'm looking at page 96 in your text. And let's see here if this comes. There we go. And so these were the main ideas of Dalton's atomic theory. First of all, Dalton theorized that each element is composed of tiny indestructible particles that he called atoms. Secondly, all atoms of a given element have the same mass and all other properties that distinguish them from atoms of other elements. And thirdly, and this is probably the biggest one right here that Dalton used, and that is that atoms combine in simple whole number ratios to form compounds. And so again, this one right here, number 3, is probably the most important piece of Dalton's atomic theory and the piece that he used as that evidence. And we often refer to that piece of evidence as the law of definite proportions. The law of definite proportions. And the law of definite proportions goes by some other names. Sometimes it's called the law of definite composition. Sometimes it's called the law of constant proportions or law of constant composition. So definite or constant, sometimes proportions or composition used as words to replace it. So it doesn't really matter what we call that law. This is what I like to call it. But one such example of this might be if we were to look at the composition of water. And if we looked at the composition of water, remember that the formula of water is
H2O.
H2O. And in H2O, what we found out was this, is that there was 8 grams of oxygen for every 1 gram of hydrogen. So 8 grams of oxygen for every 1 gram of hydrogen. And it didn't matter where that water came from. Remember that in the early 1800s now, we've started some world travel. And people now have been to all parts of the earth. And when water samples collected and analyzed, it was found out that that variation didn't change. There was always 8 grams of oxygen for every 1 gram of hydrogen. Now, the one thing where Dalton was wrong, though, is that he wrote a formula for water that looked like this, either HO or OH. What he assumed was that an atom of oxygen was 8 times heavier than an atom of hydrogen. Today we know that's not the case. If we look at the periodic table, what is the difference in mass between hydrogen and oxygen?
It is 16 times greater roughly.
It's about 16 times greater. And the reason why today we know it's 16 times greater, not 8 times greater, is because water molecules actually contain 2 hydrogen atoms for every 1 oxygen. But at the time of Dalton, he didn't realize that. He thought that he was dealing with oxygen or water molecules that had 1 atom of each. But his results still showed then that this ratio was an 8-to-1 mass ratio. And furthermore, what was known at the time was the law of multiple proportions. And the law of multiple proportions looked something like this. What was known at the time of Dalton was that there were 2 compounds of carbon and oxygen. So again, there are 2 known compounds of carbon and oxygen. And if we were to look and analyze these 2 compounds, we'll call them compound number 1 and look at compound number 2. Here's what we have. In compound number 1, it was found that there was 8 grams of oxygen for every 3 grams of carbon. And in the second one, there was 4 grams of oxygen for every 3 grams of carbon. And when these compounds were analyzed over and over and over again, it was very consistent. So in terms of the law of definite proportions we looked at first, this ratio remained constant, this ratio remained constant. But now if we compare these two ratios to each other, how does this first ratio compare to the second one?
The first ratio is twice as big.
This first one here is twice as big as the ratio for the second one. And if the first one is twice as big as the second one, that must mean that this first one has how many times more oxygen than the one over there?
2.
2 times. And so now if you know a little chemistry, even not a lot, this first one is a compound we call
CO2.
carbon dioxide. The second one is
Carbon monoxide.
carbon monoxide. So these are what the two compounds are, carbon dioxide and carbon monoxide. And this is the reason why there is a 2-to-1 ratio in terms of those two ratios there. So 2 to 1. And so this was the primary thing that led Dalton to indicate the existence of atoms. That they must exist, because it wasn't like one was 1.9 times as big or 2.1 times as big. It was exactly 2 times bigger than the other. If it's exactly 2 times bigger than the other, it must be showing that there's exactly twice the number of oxygen atoms bonding with an atom of carbon than there is in the other one. So, again, that was the primary piece of Dalton's atomic theory. Now from here, we will go on probably on Thursday looking at a little bit more comprehensive atomic theory. What I'd like to do here today is this. I'd like for you to pull your periodic tables back out. And we're going to look at these in a little bit more greater detail. And I think I'll just put in another one here at the end. So, what we're going to have in here is a quiz on the elements. I believe we told you that on day 1, and we did tell you what you're going to be responsible for. And so just to kind of review what you're responsible for, you're going to be responsible for knowing which 2 things? The chemical symbol and the name. With the correct spelling, exactly. So the name of the element with the correct spelling and the correct chemical symbol. And please note that the chemical symbols, when we write them out, first letter is always capitalized, second letter is always lowercase. And something like this would be important because if we write it like this, CO, it is cobalt, but if we write it like this, it is carbon monoxide. So we want to make sure that we do know the case. We do a little better than we did 10 years ago when texting first came out. Everybody was using lowercase or whatever. So that was a big issue, but today I see a little bit better with that. And we talked about the reason why spelling is important, because sometimes the difference in one letter conveys a different meaning in its composition. And the ones that you're responsible for, again, are the ones that are shaded in gray. And we'll talk about those here in just a bit, but the element quiz that we'll have is going to be a week from today. And that day then would be Tuesday, January 31st. And the way it's going to work is that you will get one of 2 things. If you're provided the symbol, you'll need to provide its name with the correct spelling. If you're provided its name, you'll have to give its symbol. And it could have anywhere, there's about 40 some that you're going to memorize here. That quiz will have somewhere from 10 to 20 of those elements. So it will not be over all 40 some. It'll be 10 to 20 that have been selected out randomly for you to know. Now, some other things that you should know about the periodic table itself. This will not show up on the quiz, but things that we will need to know, because we'll be talking about these throughout the semester. The terms group and period. And so now what we're looking at here is going to be independent of the quiz. It will show up on our first exam. But now the groups, these refer to the vertical columns. So these are the group numbers. They're numbered from 1 through 18. So the groups here, these are the vertical columns. Sometimes we refer to them as families of elements. Instead of groups, we call them families. And that's because elements in the same group tend to have similar chemical properties. So what we observe for lithium is a similar property for sodium. It's a similar property for potassium. What we observe as a property of phosphorus is similar to a property of arsenic. So again, elements in the same group tend to have similar chemical properties. Then the periods, these here are the horizontal rows. So again, the periods, these are the horizontal rows. And you'll see that the periods here are numbered from 1 through 7. Now, these asterisks and double asterisks we show here mean that these here with a single asterisk belong to which period? Number 6, and these here belong to period number 7. So again, you look at the asterisk there, they indicate that they're kind of footnoted. And the reason for that, and you'll see a similar footnote over here, is that if we looked at the actual periodic table, if we want to write it out properly, the periodic table would be super wide and kind of short. But we footnote them because, for one thing, you look at these elements, how many of these are common elements? Not many. So we kind of treat them less special. We kind of footnote them down below. Uranium is probably the one that you've heard of the most in here, and it's the only one that we're being asked to memorize. Other than that, we put them down here because then it fits on a nice 8.5 by 11 sheet of paper that will fit into your textbook or your notebook or whatever else. And so that's the main reason why they're not common. And if we didn't footnote them, we'd have a really wide and a really short periodic table. Now, some of the features of this periodic table. We have this feature right here. You notice there is a staircase. Anybody know what that staircase does? Divides the metals and nonmetals. Where do we find the metals?
Metals on the left side.
Metals are over here. So that staircase divides metals and nonmetals. On the left-hand side, we find the metals. On the right-hand side of the staircase, we find the nonmetals. So again, we have metals and nonmetals. And I'm going to put these in blue here. So metals over here, nonmetals over here. There's one exception to that. There's one nonmetal that appears on this left-hand side of the periodic table.
Aluminum.
It is not aluminum. On the left-hand side. I might have heard it. Yes.
Hydrogen?
Hydrogen.
Oh, that's right. Never mind.
Hydrogen. This is the only nonmetal that appears on this side of the periodic table. And then we have some elements that are right along the staircase that have properties of both metals and nonmetals. And these elements are ones that we call metalloids. We call them metalloids. And so they're ones that appear immediately to the left or right of that staircase. Aluminum, though, we don't include in there because aluminum we classify as a metal. We know aluminum. Aluminum is a metal. But other than that, elements that appear immediately to the left or the right of that staircase have some metal-like characteristics, some non-metal-like characteristics. We call them metalloids. While we're doing this, I'm going to go ahead and pull out, I forgot to bring this out here, I have some examples of these elements. I'll do that in a bit. Let's just finish this here. Let's look at another term. We have the elements of group 1. Elements of group 1, we refer to these as the alkali metals. Now the alkali metals, of course, if they're metals, they cannot include which element? Hydrogen, because hydrogen is a
gas.
Gas. It's not a metal, it is a non-metal. So alkali metals actually begin with lithium and go on down from there. The elements of group 2, these elements here are called the alkaline earth metals. So alkaline earth metals. And then if we skip over to group 18, these here we refer to as the noble gases. And then the elements of group 17, these here are called the halogens. Group 17 are called the halogens. And then we see these B groupings, and I'll put this in green. I know some of you might be colorblind, but those that aren't, this is green. And the B groupings, these elements here are called the transition metals. So we'll kind of put it like this. These here are the transition metals. Whereas those here that have the A groupings, and which color am I not using here yet? Let's try gray. So the A groupings, these here and these over here, these are what we call the main group elements. They're called the main group elements. And so again, they're the ones that are designated by the letter A. So that's these here and this block here, letter A as well. Transition metals, these are the ones that are designated by the B groupings. And then if we skip down below, elements 57 on through here, these are often referred to as the lanthanides, the lanthanide series. And the elements that begin with actinium, these are often called the actinides of the actinide series. And collectively together, if we looked at all of these here, these are often called the rare earth metals. And so while you're writing that down, I'm going to go ahead and grab some elements back here. And we're going to see how well you know some of these symbols. And so I'm going to pass these around here. And when we pass them around, just pass them around all the way to the back and up to the front over here. And so the first one we're going to look at is going to be the element with the symbol of Bi, which is bismuth. And one of the things you're going to notice is that bismuth is a very dense element. Another one that we'll show, and these two are often confused with each other, and so it's my job here to help you learn these. We have this one here, which is Mn,
Manganese.
which is manganese, and Mg, which is
Magnesium.
magnesium. So what I'm going to do here on your periodic table is I'm going to indicate to you which ones you should spend some special time, because they get confused. So Mn and Mg. Mn and Mg. Again, Mn is manganese, Mg is magnesium. Some of them that we might have difficulty with would be ones where the symbols don't necessarily align with the name. Na is sodium, K is potassium. Now where does the Na and the K come from?
It's like the Greek lettering.
These come from their Latin names.
Latin name.
They come from their Latin names. So the Latin name of sodium is natrum. The Latin name of potassium is catrum. And sometimes, though, those Latin names make sense. So one of them that we're going to look at here, where the Latin name should make sense, and I'll show you why it should make sense. is Pb. Pb stands for
Lead.
lead. But here's now why it should make sense, because the Latin name of lead is, anybody know it? Yeah. Plumbum. Plumbum.
Plum bum.
Plumbum.
Plum bum.
So it's just like plum, and then you're a bum. Okay, so plum bum is where it comes from. Now here's though why it makes sense. First of all, what do you call those pipes that run through your house?
Bum.
Plumbing, exactly. And what did plumbing used to be made out of? Lead. You maybe have heard about the term lead pipe before. That's because pipes used to be made out of lead. And they were made out of lead for a very simple reason, is because lead is something that is very malleable. It's something that you can mold and bend and whatever else. Another thing we can do with lead is this. I'll take a small piece out of here, and we'll put this up on the dot cam for you to look at. But if we take a piece of lead here now and go here, we can see that we can write with it. And so if you hear the term pencil lead, the term lead came from the fact that lead actually used to be made out of lead. And in your house, the plumbing actually used to be made out of lead, or plumbum, which is its Latin name. But now, of course, what do we know about lead? Poisonous, especially long-term exposure. And so if you have water sitting in pipes, that will leach the lead out of there. And they used to have, like when I was a kid, they talked about lids gnawing on lead-based paint in the walls, and it would cause lead poisoning. So we replaced that lead with copper pipes, and now most people are getting some PVC pipes put in your house, which is some type of plastic polymer. But your pencil lead today isn't lead. Anybody know what your pencil lead today is?
Graphite.
Graphite. And graphite is actually the element C, which is?
Carbon.
Carbon. Exactly. And so if we take a piece of graphite here now, which I have a large piece of carbon, I can go ahead and draw with the graphite that's on here. So C carbon graphite is this. And graphite is actually pure carbon. Pure carbon comes in two different forms. One of them is graphite. Anybody know the other pure form of carbon? Yes. Well, it's not a gas. The other pure form, some of you are wearing it.
Like clothes.
Diamond.
Diamond, oh.
Diamond is pure copper as well. And so actually if you compress, if you ever watch like the Superman movies, Superman will take the carbon and compress it down, and eventually will wind up forming a diamond out of it. Okay? Now a couple other that are commonly confused are these two. We have Cu, which is
Copper.
copper, and Co, which is
Cobalt.
cobalt. So Co and Cu. And we'll put these back up here. So Co and Cu are commonly confused. Cu comes from the Latin name cuprum, and of course Co for the cobalt. We talked about silicon. Silicon, if we classify silicon, of course silicon is a symbol of
Si.
Si. Silicon is which type of element?
It is
It's a metalloid.
or metal.
And so if you take the silicon out, you can look and see that it has some very distinct metal-like properties. It has this shiny metallic luster, but it does not conduct the electricity very well. We have to actually dope it with some impurities so it becomes what we call a semiconductor. And which of course semiconductors are used where? Computers, phones, any type of microchips have in them a whole bunch of silicon that we have doped with small amounts of impurities. Another interesting one here is Sn, which is tin. Comes from the Latin name stannum. If you want to pull that up, you can look at it. You can see tin is also a very malleable metal. And I think those are all that I'm going to pass around here for today. But if I go beyond the commonly confused ones of magnesium and manganese, here's a couple other commonly confused with each other. They are P and K. P and K. P is phosphorus. K is potassium. Here's the most commonly misspelled element, and this is one that you're going to want to practice several times. That is the element fluorine. Fluorine is the most commonly misspelled element. And we spell it F-L-U-O-R-I-N-E. It's not flour, like baking flour, F-L-O-U. It's F-L-U-O. And the easy way to remember that is don't pronounce it as fluorine, pronounce it as fluorine, which is the correct pronunciation. It's fluorine. And so it's just like you have the flu, which is F-L-U. So it's F-L-U-O-R-I-N-E.
Flowering, I like it.
The hardest one for many to pronounce is this one, M-O, which is molybdenum. Molybdenum. And it's also a tough one to spell, but sometimes you need little handy mnemonics to learn them. And a handy little mnemonic for this one is molybdenum. Molybdenum. Molybdenum is, if you think of it that way, molybdenum comes easy. Sometimes you come up with little jokes. Like, what do you do with a dead man?
Bury him.
Bury him. Of course, what is the last words of a dying man? Iodine. Okay, so sometimes, again, little strange things will help you learn them. And sometimes you just need a handy little mnemonic like this.
Or do you want to hear?
Hey, you! It's gold!
Want to hear sodium choke? Nah.
Ag, it's just silver. So AU, it's gold. Ag, it's just silver. And then you'll have those two down. So, a week from today, we'll have the element quiz. You will need to know the name of the element, the correct spelling, and its atomic symbol. Any questions? Yes, sir.
What was the A groups called again?
Which one?
The A groups.
A groups. Those are the main group elements. Those are the main group elements. Right up here, main group elements. Anybody else? All right. Rare is it that we get out early, but today is one of those days. Just make sure I get the elements back up here in the front. That's it for today.